Hello, guys. Welcome to another probability class. If you can, please turn on your camera so I may look at you. I already see a little bit fewer people, and I suppose that's because today is a very sad day. Today, we part with combinatorial analysis. Farewell to combinatorics. So that the party, like in Ernst Hemingway's Farewell to Arms, right? So that the party isn't too quiet. Let's try to see what combinatoriety has been. Let's celebrate all the beautiful aspect of its life before we move on. And with that, first question, 52 cards to be divided equally among 4 players. How many possible outcomes? You understand, guys? So 52 cards equally divided among 52 players. How many possible outcomes are there?
Each player gets the same number of cards, correct?
Yes, that's what equally mean by equally. So each player has the same number of cards, namely 13 cards, if I'm not mistaken. Good. So quickly, guys, in the comments, type the solution, and I will go over it in a moment. Sorry that I hurry you up so much. It's just that time is very restricted. All right, Gustavo, you have 2 solutions that you offered. Camille, you offered another solution, right? So of course, we have to be sure that we understand the question correctly. Let's see the situation, guys. So the way I would solve it is make a Kafka protocol, because even if I misunderstood the question, at least the Kafka protocol explains exactly how I interpreted this question. Yes. So the way I interpret this question is player 1 is a dragon, player 2 is a dragon, player 3 is a dragon, and player 4 is a dragon. And the knights, in that analogy that I use, the knights are the different cards. Yes. So each of those boxes will receive codes listed from smallest to largest number, right? So in other words, there is smallest to largest number in the red box, independently smallest to largest number in the blue box, and onwards. Yes. So this is the red tray, the blue tray, the green tray, and the, I don't know, purple tray, whatever that color is. And this is the multinomial coefficient 52, choose 13, 13, 13, 13. 52 cards divided among 4 destinies. Yes. Or 52 factorial divided by 13 factorial to the power of 4. Make sense, guys, how this is calculated? Why 13 factorial to the power of 4? Because if we use a 52 factorial, we arrange the cards in a sequence, right? And then we can move them around within each tray. So the first 13 cards in that sequence can be permuted without changing the outcome. The next can be permuted independently of the previous permutation, and the result is not changing the outcome. So that's why we divide by 13 factorial to the power of 4. That's to eliminate overcounting, right? 13 factorial to the power of 4 is how many linear sequences represent the same situation for each different outcome. Very nice. Now, a slight modification of that problem is then to try to understand what happens if we simply divide into equal piles, but not give them to different players, right? So I just want to have a pile of 13 cards, another pile of 13 cards, and onwards. And it doesn't matter what order the cards are listed in this pile. Okay, thank you, Joseph and Ryder. be careful. There is maybe what you're thinking is, I guess there's something you forgot to type. All right, so let's see the situation, guys. It's very like what we did before, very similar to what we did before, except now I can scratch away. I can take the same form, but I can strike through P1, P2, P3, and P4. They are no longer distinct categories, right? So what all that matters is that whichever sequence is in each box, it just, you can move it now around. You can now move those red box and blue box, and you can permute those, and that does not change the situation. So it's the same result as before, but divided by 4 factorial. Before I move on, guys, so just a quick check. Is it clear? Type Y for yes, it's clear, or do you need more explanation, please? All right, guys, I do hope that means that it's clear. And if not, you can always, if you somehow don't feel comfortable or you're not sure what to ask, you stay after class. I will be happy to help. Now, here is a modification of that problem. 52 cards, now to be divided among 4 players, but each player may receive 0, 1, 2, 3 cards and onwards, right? There is no limit to how many cards a person receives. The numbers that each person receives does not have to be equal. Somebody might receive nothing, somebody might receive everything, it's fine. Always, guys, regardless whether you see the answer right away, write your Kafka protocol or have it in your mind. Well then, let's look at the solution. You see, in this situation, each card can go anywhere it likes. So card 1 can go to player 1, player 2, or player 3, or player 4. Regardless of what card 1 did, card 2 can also do the same, can go, it has 4 possibilities. So you see, what do we have? We have 52 boxes for each card, and within each box, I write numbers 1 through 4. So for example, the code 44444 repeated 52 times means that player number 4 received all the cards and the others got nothing. Yes? You understand what I'm saying? Yes, guys? So the code here are strings of numbers that are, the string is 52 symbols long, and the string is made out of 1 through 4, of the numbers 1 through 4. And so there are 4 possibilities here, 4 possibilities in the next situation and onwards. So the answer is 4 times 4 times 4, 52 times, or 4 to the power of 52. Do you understand? You understand, guys, how you solve this problem, right? I always try to visualize what a code might be, right? So the code, I read this code and I understand how the cards were divided. So my code is 52 strings long, symbols long, a string is 52 symbols long, and it's made out of numbers 1 through 4. Good. I hope you understood. The next question is 52 cards divided into 4 piles. The piles are not necessarily of the same size. Now, this might be a very hard question. So you understand it's not the players, the cards are divided into 4 piles, and the piles are not of the same size necessarily. So how many piles are possible? It's perhaps very unfair that I ask you this question with such little time to think. All right, guys. So I suppose I will go over it unless you want me to preserve it for another day. So no objections, I'm going to go over it, yes? All right, so this question is such that using just simple combinatorics, I cannot answer it. At least if you can come up with something else, that's wonderful. This is how I thought of this problem. You see, I need to count piles, and you realize that certain types of piles are more frequent than others, right? Certain types of piles are more frequent than others. So it's very difficult to count directly. But so I develop this recursive formula. So let's, in general, imagine that we have n entities that we wish to divide into k piles. I represent the number of possibilities with n sub k of capital N sub k of little n. Yes? You understand what it means? This is how many piles I want, and this is how many objects. So let's see what happens when you have a simple situation. So for example, capital N sub n of n, obviously 1, because it means divide n objects into n piles. You agree? And that means that each pile receives 1 object. And we don't really care about the arrangement of the piles, right? There's no such thing as pile 1, pile 2, pile 3. All that matters are your friends in the pile, right? It's floating in space. There is no, it doesn't matter if person 1 and 2 is in one pile and 2 and 3 in this pile, or vice versa. It's the same situation. It's the same pile arrangement. So this is 1, and clearly n sub 1 of n is also 1, because that means put everything in one pile. There is only one way to do that. Also, if k, the number of piles, is bigger than n, then it's impossible to do that. So the answer is 0 ways to do it. Yes, you agree? So if there are more piles than actual objects, I cannot do it. So then I arrive at the following recursive formula. So you can just take n sub k of n. That will be n sub k minus 1 of n minus 1 plus k times n sub k n minus 1. Now, how do I come up with this formula? Very simply. Think about it, guys, right? So if I have n piles, sorry, if I have k piles, and I focus, remember what we did with Jimmy, right? Jimmy was a special boy, and we focus on Jimmy selected or Jimmy not selected. So in this case, the element n the object labeled as n is the special object. So I wonder, is this in my piles, I can group them into two categories. The piles where n is lonely, where Jimmy is lonely, and the piles where Jimmy is with friends. Right, so it's like we divide the class into groups. I think it's the same thing, right? Divide the class into groups, and the groups could be of a solitary individual. Now, we want to know the groups that Jimmy is solitary or Jimmy is together with others. Good. So this so you understand, guys, that if Jimmy is solitary, then I just have to divide the remaining objects into k minus y piles, k minus 1 groups. Do you agree? Jimmy is solitary, so we have already accounted for one group. And the remaining ones, there are n minus 1 objects still to be distributed among groups. And the number of groups remaining is k minus 1. Are you with me? So you understood why the left is true, why this part of this formula is viable, what this means. Plus, now think about what happens if the nth object is not lonely. It's not by itself. That means that we have, that means what? That means that we can imagine initially just calculating how many ways is there to create k groups out of n minus 1 objects. Yes, imagine, and then for each such group, I can throw the last object Jimmy into group 1 or group 2 or group 3 or all the way to group k. There are k places where I can throw it. So for each group that in my count for n minus 1 objects, if I toss Jimmy to one group or another, then I create the extra k. That's why I multiply by k here. Do you understand? So what I do is Jimmy alone plus Jimmy not alone. Now, if Jimmy is alone, that means that I have to divide n minus 1 individuals among k minus 1 groups. Yes, and I count how many ways to do that. If Jimmy is not alone, I can imagine taking Jimmy out, dividing the remaining people into groups, and then either inserting Jimmy into first group, second group, third group, all the way to k group. Right, where group is defined by the individuals in it. You see, so that creates and it multiplies the number of possibilities by k, because each situation I have k possibilities for it. Right, each node, imagine having those dots. Each dot represents a node, a particular division. For that dot, Jimmy creates k extra possibilities. It splits into k possibilities. For that dot, Jimmy is in first group, second group, third group, and onwards. Yes, do you follow? So this is my formula. So how it works, then you can just use recursion and calculate it. So for instance, if I want to calculate for a smaller number, how to partition 4 objects among 3 piles, 3 groups, then I can do it as follows. I can first calculate based on this. I need to calculate n sub 2 of 3, this part, n sub 2 of 3. That's where that's easy to calculate, because that means that that Jimmy, the object number 4, is alone. So if he's alone, then we have either we have 1, 2, and the other lonely object is 3, or 1, 3, the other lonely object is 2, or 1 is the lonely object. You see, so it's easy to just calculate directly. You don't have to do it. You can just again do recursive formulas until you reach to a situation where the answer is obvious. You see, because you would always remove something either from here or from here, right? So you can eventually reduce the possibilities to something that you can count, right? So here I kind of explain the other part. The other part is where the other part is this n choose k. So that would be 3 of 3 multiplied by 3. And that's because you see, so if we have 3 groups and he's not alone, then he is either in this pile or in that pile or in that pile. So there are 3 possibilities. And 3 of 3 is 1, and then just multiply it by 3, because you either place him here, or you place him here, or you place him here. Yes? And here I carry out the calculation. Sorry?
Okay.
Yes, good. Did you understand, guys, or barely?
It makes sense. It's just a bit. I haven't looked at recursion since spring semester, so it will take a minute to,
Yeah, it will take maybe more than a minute, but you can think of it. It's just at least I did not figure out a way to do that without recursion. That's all I can say. Maybe there is a better way. Yes, right. All right, so then the next question is question number 5, hopefully a little easier. By the way, guys, just as a census, write Y if you understood or N if you did not understand the explanation of the previous problem, just to see how the explanation, how I'm doing. Okay. 2 people say they don't understand, and the others, what about the others? Too confused to, it's something between yes and no. All right, so I'm doing pretty well. I guess most of you did not understand so far. Let's move on then. So yeah, 52 cards are dipped in black ink. They are no longer distinguishable. How many ways of dividing them into 4 equal piles? Do you understand the question, guys? So we no longer regard them as different cards. They are like George Washington's, like individual dollars. Even though the miser would say that each George Washington is like another son to him. But here we don't distinguish them. And the question is how many ways to divide them into 4 equal piles. Equal piles, guys. Okay, I have 2 answers. Good. More? So yes, I have a few people answered it correct. And the answer is everybody who did decide to write something appears to me to have answered correctly, because you see, guys, there is no need to do any complicated division, 13 to each, right? It's like if you have a pile of 52 Benjamins and you just give each person a Benjamin, 13 of the Benjamins, right? Yes. Only one way. Now, the next question, 52 black cards, and they are not distinguishable as before, are divided into 4 possibly unequal piles among 4 players. You understand? So you can eliminate piles that are divided, but not necessarily equally among 4 players. How many outcomes are possible? Always, guys, always write a Kafka protocol, because so far I'm seeing answers that are incorrect. Maybe one answer was correct, to be just me not jump. No, I mean, I think all the answers are incorrect. 52 cards divided among 4 players. The cards are the same, guys. It's not, they're not different, right? Imagine that the cards now were turned into unit dollars, right? So it's $1, another dollar, and then you divide it among the players. Each player gets one pile, precisely, Grant.
But kind of looks like early problem. Like
of course, it should look like an earlier problem, right? Although from the days of yore, since I haven't seen you in a while, right? I haven't seen you a week or so.
Oh.
Yes, I've seen many things, so it felt longer. I've seen beavers, I've seen nature. Yeah. Okay, Barry, you're getting there. Stephen, why? I don't understand. What problem does it remind you of, guys? One of the big problems of civilization is people have such short memories. Well, Albert, you must have a much better memory than me because you say problem number 2. I don't know what problem number 2 is. Do you remember Hans Christian Andersen? Yes? So that, yes, exactly. So the mermaid and the foam, but specifically the matching girl, the little match girl, or the hypochondriacs that go shopping for toilet paper. Yes. So the situation is, there were a few people that answered it correctly. And that depends on the interpretation, guys. So we have xk is number of cards assigned to player k, where if we assume here k is bigger than or equal to 1, so we have x1 plus x2 plus x3 plus x4 equal to 52, right? And that means that there are, I say clearly, 51 choose 3 solutions. Now, why 51 choose 3, guys? Remember how we can calculate this. we can, if we are forced to assign one card to each player, we take 52 minus 4. Yes, 52 minus 4 gives us 48. Yes, and then what you have at 48 cards, 48 plus 3 bars. Remember the toilet paper. We 48 objects plus 3 bars. The 3 bars are partitions. Yes, 3 will partition into 4 segments. Equals to what? Equals to 51. Yes, 51. Thank you, Gustavo. All right, 51. Now, out of those 51, we just choose 51 what, guys? You have to remember what the 51 is representing. 51 spaces, right? So we have 51 spaces. 3 of those space slots are occupied by partitions, by those bars on the, I call it conveyor belt, right? This thing that you have in the store that looks like a treadmill. Yes, on the conveyor belt you have 3 bars. So 51 spaces, 3 of those spaces, choose them, they will be occupied by bars. Yes? Good. Now, if I accidentally misled you, I mean, I thought that I asked that some players are allowed to get nothing, you see? So I thought it's something like that each player could get 0 cards, right? So it depends on your interpretation. You know, you either give each of them at least 1, or you might even allow for 0. Yeah. So here is the next question, guys. So it has 2 parts. 10 children come to a party. 3 of them are very good friends and have to sit together. Part A, how many ways of sitting them in a row? So there is 1 row. The children must sit together, the 3 friends. How many ways of doing that, please? Right, yes. Yes, good. And we will explicitly explain how we carry this calculation, guys, right? Even if you right away see it, Kafka protocol. Nothing is true unless it's bureaucratically documented. And that's especially so for exam. Right? It's like, are you a camel? Yes, and you say, no, I don't believe you. You have to have a passport with 3 notary signatures that you are not, and other documents, and documentation, as you understand today. Yes, we'll get to part B in a moment. Yes, we're looking to sit 10 children. I'll explain to you how I think of this problem. Ready? I'm just explaining part A. We are going to try to do B in 1 moment. So for A, the Kafka protocol is as follows. I imagine, since those are good friends, I imagine I will, first of all, isolate the group friends, and I will tie them together. I will create like a human centipede out of those 3 friends. And here is one arrangement A, B, C. I create a super friend. I create 1 object. Yes? So before we used to have 10 objects, right? But here I have first instructions on how to combine them into 1 being. Secondly, is now this being is labeled as 1, and all the others are relabeled to be 2, 3, 4, etc. So altogether, we now have 7 plus 1 or 8 objects. Do you see? So rearranging them, it's 8 factorial, and the extra 3 factorial is instructions on how to create the 1 friendly being, a global being. So here it is, guys. Here is my Kafka document. You see, friend A, B, and C, that's this arrangement. And then this is where the clusters are. So this is cluster for the friendships, for the friends, 3 friends, and then the other clusters, yes? So we have 8 factorial, 3 factorial times 8 factorial. You see why? So you have to have an explicit Kafka protocol, and that makes things much easier. Wonderful, good. All clear, yes? All right, guys. Now, the somewhat harder question is how many ways of sitting them on a merry-go-round? And we want to create we want to understand mathematically what is a merry-go-round. Yes, Cindy, that is a circle, but what does it mean? What is the difference between a line and a circle, really? Very good, no end or beginning. No stop or stop, or you can decide where stop and stop is. You understand? When it's a line, this is the start, this is the stop. But if it's on a drum, if it's on a circle, then you can arbitrarily decide where start and stop are. Yes? So this is the important aspect here, guys, right? So here is the idea. So here is a word written on a piece of paper, right? It's made of letters A, B, C, D, right? So here is the beginning and here is the end. Now, what happens if we make a merry-go-round out of this paper? Then the letters are written on this piece of paper this way. Do you see? The start and end are merged. I drew it as a dotted line. Yes? So interesting. Somebody says 3 factorial, 7 factorial. Okay, we'll see in a moment. Get ready, guys. And other solutions. So first we are trying to understand it. You see, guys, now when I see it move around, the words A, B, C, D, B, C, D, A, C, D, A, B, and D, A, B, C are the same because they represent the same pattern. You see, why are they different words? Because I now am free to choose where I want to begin to read the word. Right? If I decide to start with the letter A, it's going to be A, B, C, D. But if I decide to start reading this word from B, it's going to be B, C, D, A. Can you see that? You see why they're different words? Yes. Start stop position is gone, but guys, one extra idea is that you are now free to decide where start and stop is, right? Before it was imposed on you in a linear order, but now you can decide where you would like to start from what. Yes, when you try to read the pattern, you can decide for each situation where do you begin. Good. So the differences here are just difference of where you decide to start, but since there is no objective start or end, they mean the same thing, they're the same arrangement, yes? So that means that I might decide to always start when I see merry-go-round from position 1. You understand? I mean, if I see the friends spinning, I can basically, you know, here I'm looking, I'm this parent looking at this group of people that I supervise. And let's say I imagine that the friends are wearing, I don't know, a red shirt, all of them, right? So I begin counting when I see first red shirt, third red shirt, fourth red shirt. You understand? First, second, third. I'm sorry, right? First, second, third. So that's where I begin to count. From the first moment when I begin seeing the category, if they're sitting in the way I assign them to sit, I can begin with category 1. You see, so that means that in my permutations, I can assume that I can use the same formula, but now the items are beginning to be, they begin from position 1. So this is filled in. I have 7 factorial positions available. So it's 3 factorial, I still arrange them relative to themselves. It still matters if I read this word, if I begin reading it like this, as the merry-go-round spins, I read it like this. So I might see A followed by B followed by C, or I might see C followed by B followed by A, and that's a different arrangement. Do you agree? That's a different distinguishable pattern of seating them. So all it is that I still have 3 factorial ways of making them into a super friend, into one object, into one category, but then I can begin reading from that one category. So it's 1, and then we have 7 available items. So it's 3 factorial times 7 factorial, as I've seen at least one person respond. Do you understand, guys? If not, of course, I'm very happy to re-explain. All right. Now let's try to generalize the situation, guys, for problem 8. Right, so we don't want to just solve this problem for, yes, you choose the starting point, and the starting point is also the end point because it's going a circle, right? So that's where you start reading it, and that's the distinction that's useful here. So suppose now that we just had the summer, summer is over. We have n children, and 1 of them are in camp 1, and 2 of them are in camp 2, and k of them are in camp k. In other words, everyone is in some camp. Yes? And you can imagine that they are distinguished by the shirts they are wearing. So imagine that one camp is dressed in yellow, and another is dressed in all red, just something that you right away see where they belong. Yes, where they belong, and then how many ways is there to sit them if all the members of the same camp must be together, and we want to sit them in one long row? You understand? So members of one camp are together, members of another camp are together. They cannot be separated. How many ways of sitting them? Can you tell me, please? It's a general formula, right? So it's a bit annoying to type, I bet, right? But you understand, we have n1, n2, and all the way to nk. That's how many entities are in one cluster. Think about the form, guys. What do you do for solution A? Here is, it will help you to learn German, guys. Then you will really be very good at placing people in camps. So this is camp 1, camp 2, camp 3. Yes, and onwards. So you can see that this is the arrangement of the first cluster, second cluster, and onwards. So there are n1 factorial all the way to nk factorial arrangements of them separately. You can enroll into German with me if you want, all right? I will give you a Duolingo course if you want, all right? Wenn du willst, wir können einfach nur auf Deutsch reden. So we have all those arrangements. We have n1 factorial, and 2 factorial, and 3 factorial, and onwards until, and this is the order of the camps. How do we place the camps in a row? First camp, second camp, is what goes in which order, right? So what do you have there? There are k different camps. So that's where the k factorial comes from. And those are the arrangements of entities into clusters. All good, guys. You want to practice with me, you can see, right? So if my goal is, of course, to be your entire library, right? So not just probability, but everything else, right? So ideally, you come to me like into a supermarket, like into Costco for all your needs. Good. So here it is the solution. Are we clear? Wonderful. So now, guys, we would like to place them all on a merry-go-round. Can you help me do that? By the way, who teaches you German, guys? If you're learning German, by any chance, Elke Nikolai, anybody I know? What's the instructor? Yes. Say hello to her if you ever see her. Yes, the number within a camp factorial because you place them as a block. That's how you place them as a chunk together, right there. And then okay, very good, Camille. Yes, right. So it's the same situation from before, but you see, we are now free to say, I'm going to start when I see the spinning, I'm going to start looking at the counterclockwise world developing starting from camp number 1. Yes? Same form, and yes, here it is. I hope you understand, guys, right? It's, yeah, good. Here is one other question. 4 computer science, 5 math, and 10 sociology majors. Second, a question. Barry, I congratulate you as well. Sorry for failing to congratulate you. By the way, you have a nice name. Reminds me of Barry Lyndon. If you never watched the movie, make sure. It's one of my favorite movies. Do you know this movie, guys? Barry Lyndon by Kubrick. My favorite, one of my favorite movies in the English language. Yes, the Kubrick film. Good. Exactly. Oh, here we go. Here we go. Some people are understanding the quality. Yeah, very good. I like the last phrase. You remember the last phrase? It was in the days of King George, when they lived and quarreled, good or bad, beautiful or ugly, they are all equal now. Yes, yes. Now back to this problem. 4 computer science majors, 5 math, and 10 sociology are taking a 6-hour probability exam. I cannot tell students from that belong to the same category. Students look the same to me. So I can only tell them based on their, well, the species, the major that they are studying. Yes? So if I see them, if I just record which students leave at which hour, how many possible combinations do I see? Yes, they can live in any order. Each of them is presumably an individual, but they are, you can imagine that they are dressed, in my mind, they are dressed in particular shorts, right? So let's say maybe the math people are blue, I don't know, because it's hard, right? Sociology people are red because they're angry or not, right? So you have them dressed somehow so that you can just tell in which order they live. They could obviously live all at the same hour. But basically in my recording, I say, let's say 2 sociology students finished, 2 sociology, 1 math student, and maybe 3 computer science students finished within hour number 1, right? And then how many finished in hour number 2 for each category? That's how I understand this problem. Good? All right, let's do it together, guys. Or, yeah, I'm sorry I hurry you so much. It's just as I told you, I never managed to cover enough material. So this is how we understand it. So I color red, computer science majors, math are blue. And yes, I guess sociology don't deserve a color. So then we have summation is a summation of x1 all the way to x6. What is x1, guys? X1 is, so 1 through 6 is the hours, yes? The hours, first hour, second hour, third hour, fourth, and onwards, yes? The hours. And X1 represents how many computer science majors first hour gets. X2 represents how many computer science majors the second hour gets, you see? Okay, so in this case, the hours are my hypochondriacs and the students are my toilet paper. Good? So the same thing we have for the second category for math and for the sociology people. Yes? Clear, guys? You see what's happening now. Now, each of them we can calculate as a separate experiment. Yes, so we already, it's basically solving the same type of question, but 3 times, and then multiplying the results. It's basically how many people from one category the hour gets is not affecting how many people of the other category that same hour gets. Yes. So I just solve the number of solutions for each of the equations, and here is what I get: 4 plus 5 choose 5, 5 plus 5 choose 5, 10 plus 5 choose 5, right? And it's 9 choose 5, 10 choose 5, 15 choose 5. Makes sense, guys? Why it's plus 5, right? Why it's plus 5?
5 is the number of gaps in the hours.
Yes,
correct?
very good, right? So we have 4, yes, something like that, right? Right. So you see, we have to partition it into 6 parts. We need to have 5 bars, and we have 4 objects in this case. So 4 plus 5 choose 5, right? That's how many spaces. Choose 5 spaces. Very good. Are we understanding? Beautiful. Very good, guys. I'm very proud of you. Now I will briefly stop this video and we begin reviewing. Information from calculus. Let's see how well you remember the basics of calculus or infinite series very specifically.